So I'm going to change my share to this. And so this is number 2 from the homework. And we're looking at which ones of these are likely to form or which ones are unlikely to form. I'm going to try and get this to focus. Okay, so let's take a look at potassium. Potassium is a 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. That's potassium neutral, right?
Yes.
Okay, so here, if we want to make a potassium plus 1, we'd be making a 1s2, 2s2, 2p6, 3s2, 3p6, and the 4s1 electron would be taken away because we take away the least stable electron to make the ion.
Right.
To make a potassium 2 plus, you'd be taking a 1s2, a 2s2, a 2p6, 3s2, and then this would be a 3p5. So I'm going to add a little bit here. To turn this into this, we have to take away a 4s electron.
Yeah.
And to go from here to here, we have to take away a 3p electron. Well, the difference in the amount of energy to take a 4s versus a 3p is just phenomenally different. So that's why this wouldn't happen. You could also add that furthermore, when you take away one electron, you get the electron configuration of krypton, which is stable. And for some reason or other, when you reach the noble gas electron configuration, it's stable. And we're going to learn that it's because of something called the octet rule, which you've already heard of. If you notice, potassium with a +1 charge has 8 valence electrons, and that confers a certain stability on atoms and ions. Okay, so that would be for this guy right here. What about cesium +1? So cesium +1, I'm going to go ahead and for this one, start at krypton. Normally you'd start at xenon for this guy, but I'm going to start at krypton. And after krypton, you've got 4d10, 5s2, 5p6, 6s1. Normally you don't want to write it right off the bat in the correct order because you're reading it off the periodic table. But in order to save time, I've just read it the way it should be. Okay, and that's cesium with a no charge. So cesium +1 would be krypton, 4d10, 5s2, 5p6, which is the same as xenon. So here, again, you've got 8 valence electrons. So you'd have to say that the cesium +1 is likely to happen.
Okay.
Okay, so this guy is unlikely, and this guy is likely. How about aluminum +4? Well, aluminum is 1s2, 2s2, 2p6, 3s2, and 3p1 is what I want to say. Okay, so let's go straight away to aluminum. It's probably better that we do these one at a time. So aluminum +1, 1s2, 2s2, 2p6, 3s2. Aluminum +2, 1s2, 2s2, 2p6, 3s1. Aluminum +3, 1s2, 2s2, 2p6. And here we've got that noble gas configuration. But let's take a look at aluminum +4 would be 1s2, 2s2, 2p5. So to go from here to here, we take away a 3p electron. Here, you take a 3s electron. Here, you take a 3s electron. And then all of a sudden, to go here, you have to take a 2p electron. And a 2 versus a 3 is just so much harder to take. There's you're not really going to do it. Okay, so can you see how we might extend down farther and farther and try to answer these?
Yeah.
Okay, so the answer of it doesn't fit the charges that we learned from chapter 3 is not what we're looking for. We're looking for context based on this chapter, which probably means electron configurations and thinking about what electrons are added or what electrons are missing. Okay? All right. How about next?
Number 4.
Number 4. Let me pull that up on my screen here so I can see it. The ionization of hydrogen atom can be calculated from Bohr's equation, blah, 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 blah. Z is the atomic number. And what do you think n sub A is?
The shell number.
No, it's Avogadro's number.
Oh, yeah.
So that's essentially 1 mole, right?
Mm-hmm.
So we know that RHC is the energy of 1 photon or the energy to take 1 electron.
Yeah.
So when you multiply by n sub A, you're multiplying by a mole. So now we're calculating the energy for 1 mole. And that's why it says minus 1312 kilojoules per mole.
Yeah.
Okay. All right. Let's use this approach to calculate a possible ionization energy for helium. First, assume the electrons of helium experience the full +2 nuclear charge. Okay, so Z is the atomic number. So what we're talking about here is Z will be 2 instead of Z star, because Z star is different, right? Z star is the effective nuclear charge. And that's why they're saying it experiences the full 2+ charge.
Right.
Okay, this gives us the upper limit for the ionization energy, meaning that if you put 2 in this equation, you're going to get the largest amount of energy. And it's probably less than 2 because Z effective is always smaller than Z.
Mm-hmm.
Okay, so this gives us the upper limit. And then it says next. So we're just going to stop there, or we're going to calculate for helium the energy if Z star is equal to 2, so to speak.
Okay.
So we've got E is equal to negative parentheses n sub A RHC parentheses Z squared over n squared. And Z is the atomic number. Now we're going to do this for helium. So we're going to do minus 1,312 kilojoules per mole, because they tell us that that's what that value is.
Mm-hmm.
And Z for helium is 2, so we're going to have 2 squared. And then we're going to say what for N?
1.
1. Because we know that helium is 1s2, right?
Yeah.
And so we're taking away a first shell electron. So here we're going to calculate that upper limit. And you can see that this answer is basically going to be 4 times this, but negative, right?
Yeah.
So 4 times this puts it at around what, 5,020, 5,200 or something?
Yeah. I got really close to that.
Okay, 1312 times 4 is oh, I knew my answer had to be wrong because it came out to be 1316. So I added 4 to it instead of multiplied by 4. See, that's why it's good to estimate. Okay, 5,248 kilojoules per mole. Okay, and if we compare that to hydrogen, we can see that it takes a lot more energy, doesn't it?
Yeah.
Because hydrogen Z would be 1, N would be 1, and it would be minus 1,312.
Yeah.
Okay, so this would be the upper limit. And when they say upper limit, they mean the most negative.
Okay.
Okay, now it says next, assume one electron of helium completely screens the nuclear charge from the other. So Z is equal to 1. So this is helium, and this is helium with screening. So the energy for the screening is going to be minus 1,312 kilojoules per mole. And they say that it completely screens, right? So we have 1 squared instead, right? Now, what does it say about N? Let's see. So it's the same.
Okay.
So we're going to get minus 1,312 kilojoules per mole. And we don't even need the calculator for this calculation, right?
Right.
So this is the lower limit. That means that this is going to be the least amount of energy needed to take that electron away.
Yeah.
Okay, now compare these calculated values to the experimental value of 2,373.3 kilojoules per mole. So I would do something like this, and I'd make this minus 1,000, minus 2,000, minus 3,000, minus 4,000. And I'm trying to evenly space these, but I'm not measuring them out. Okay, so this is about where the lower limit is, right?
Yeah.
And here, 5,248, this is the upper limit. And the experimental value is 2,372. So it is here. This is the real or experimental.
Is that so? It's supposed to be a negative value.
Yeah. Okay, so what does this tell us about the ability of one electron to screen another? Well, remember, for the lower limit, we have screening. And at the upper limit, we have no screening. Right?
Yeah.
Now, the real value is closer to the lower limit than it is to the upper limit, right?
So it's likely that it's being screened.
Yeah, so I would say that, you know what, screening is pretty effective. And here, let's write out a sentence to say that. Since the experimental value is closer to the lower limit, which has screening, the ability of electrons to screen is pretty good. And here, we don't need to quantitate it. It's pretty good.
Okay.
You know, we don't need to put a number on it. We don't say, oh, the difference here is, what is the difference? Oh, the difference is almost 1,000, right?
Mm-hmm.
So you wouldn't say, oh, it's a difference of 1,000, which means it's 5 times better or something. You wouldn't do that.
Okay.
Okay. So it's pretty good. And that's how you would answer a question like that. So you got to do this step by step. First, you calculate the upper limit, then you calculate the lower limit, then you just compare it. And probably the thing that gave you the hiccup was there was no negative there. But you got to understand that these are just energy values, and it's the negative just means is energy in or energy out.
Right. And I just wasn't quite sure how you wanted them to be compared
Okay, well,
in
in
Word.
a case like this, I think a number line is perfect.
Okay.
Okay. And when you draw that number line out there, instead of asking people to visually think about, oh, 2,372 is closer to 1,312 than it is to 5,300 or 248, to make people think about the visual versus draw it out, you're basically proving that everyone is a visual learner, right?
Yeah.
Who wouldn't like this better than being told, hey, this is closer? No one. Everyone likes this better because you take a quick look at it and go, oh yeah, it's closer to the screening one. So screening is a good thing, or screening must be a good model. So that's one of the things that you'll find in your chemistry book is lots of drawings and lots of pictures, because the visuals are supposed to help you understand things. And as students, what we're supposed to do is also emulate that and do lots of drawings and lots of pictures to help people understand things.
Okay.
Okay. All right. So that was number 4.
Can we look at number 5?
Absolutely. Okay. So number 5, the bond lengths in chlorine are 200 picometers. In bromine, they are 228 picometers. And in iodine, they are 266 picometers. And for tin, the radius is 241 picometers. 141 picometers. Okay, so they're not telling us really a bond length. They're telling us a radius, right?
Or 10? Yeah.
Yeah. Okay, so they want us to find the bond length in tin bonded to chlorine, tin bonded to bromine, and tin bonded to iodine. So the way to think about this is for chlorine. So this is a chlorine and this is a chlorine. This is 200 picometers. Okay.
Okay.
So based on this, what is the radius?
Half of that?
Right. The radius would be 100 picometers.
Okay.
So with bromine, these are supposed to be a little bit larger. This is 228 picometers. So what is the radius for bromine equal to? This makes me want eggs.
100 and
114 picometers, right?
Mhm.
And then for iodine, which is even bigger than bromine, and I'm not trying to draw these to scale. I'm just trying to make them so they look like they're getting farther and farther apart. That's all. The nuclei, that is. So this is 266 picometers. And what is the radius?
133?
Okay. So here, I'm going to try to duplicate the size of this guy where the radius is 100. So there's my chlorine, supposed to be the same size as one of these. And now I want to draw a tin next to it, which has a radius of 144, which makes me think it should be even bigger than iodine, right?
Yeah.
Okay, so I'm going to draw something here that hopefully looks bigger than iodine. And that's my tin. And we know this is 141. We know this is 100. So what is this bond length?
241?
241 picometers. Okay, so now we draw something a little bigger than chlorine. This is bromine. And here to the edge is 114, right? And I draw my tin again. And from here to here is 141. I didn't line those up too well, but you get the idea. What is the bond length here?
255.
255. And then lastly, we have an iodine, which is even bigger than bromine. And the distance to here is 133. And then we have our tin, which is even bigger than the iodine. And the distance to here is 141. So what is our bond length for iodine and tin?
174, I think.
274, right?
Yeah, oh yeah.
Yeah, you made the mistake I made over here where I just goofed up. Okay, so this is our hypotheses, right? Based on bond lengths and radii. So we hypothesize that a tin chlorine is going to be 241, that a tin bromine is going to be 255, and that a tin iodine is going to be 274. And these are all picometers, right?
Yeah.
Now, the experimental values are 233, 250, and 270 picometers. So what would be your comment when we compare them?
The experimental value is actually smaller.
It is actually smaller. Okay. So experimental value is smaller. How close is it?
Really close still.
Okay, so do we have any idea based on a real value versus experimental value, a way to judge closeness?
Yeah.
What would that be?
Like precision or accuracy?
Accuracy. So the accuracy here would be the difference between these two,
So
right?
like percent error.
And actually, I shouldn't say it's accuracy, but percent error. So the percent error for this first one would be 8 divided by 233 times 100%, right?
Yeah.
And we only get one significant figure. And we get 3%. So this has a 3% error. I think this one ends up having like a 2% error, and I think this one ends up having like a 1% error. Let's see, 4 divided by 270 times 100. I get 1.48, which rounds down to 1% for one significant figure. Okay, so what we could say is that the experimental value is smaller, and the percent error for each is less than 5%. So we'd say that, you know what, it might be pretty accurate.
Yeah. Okay.
So in this case, unlike the other one where we're comparing the energies and we don't know, you know, it's not really an accuracy type of thing. It's a relativity type thing.
Yeah.
Here we can do an accuracy type thing or percent error type thing.
Okay.
So it's, you know, always good to think about what we've done in the past and, you know, what's the best way to analyze each situation based on what we learned in the past. So that would be your answer to 5. And again, what do you think of the visuals?
It helps a lot.
And that's why people do them.
Yeah.
You know how they say that there's different types of learners, kinesthetic, visual, auditory, blah, 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 blah. It turns out that everyone learns better using their hands, everyone. And then the next best is by looking at pictures and diagrams and video and seeing something. And the worst learners are the ones that learn only by hearing. Everyone does better by touching and doing. Everyone, even the smart people that can really think about this visual or hear it and think about it in their minds, even they learn better by hands-on experience. There are studies that have been done that says that all of those different modes of learning, they aren't real. The reality is that everyone learns better by hands-on. And that's why, when you do things like nursing, you do these clinicals. You do these things where you get some hands-on experience, because you just start blabbing at the students all day long and they're going to go, I'm not going to remember this.
Yeah.
And then they look at pictures and they're going to go, okay, I'll remember this a little better. But then when you have them stick their hands on a thermometer and put it in their mouth and, palpate their pulse or something then it gets real. And this is the thing that's hard to do with a class like ours is, how do you do the real stuff? And that's the lab.
Yeah.
But even then, for some of these topics, we're not going to go have you measure the distance between nuclei. So we have to give you that information. And so this is the best we can do, the visual. Okay. What next?
Number 7.
Okay, which of the following elements has the greatest difference between its first and second ionization energies? Explain your answer. So here it says the second ionization energy is the energy required to remove an additional electron. So let's take a look at just one of these to begin with. We're going to look at carbon. So this is number 7. And we're going to look at carbon, and we're going to look at the first and second ionization energies, okay?
Okay.
So carbon is a 1s2, 2s2, 2p2. And for these, I usually like to look at the orbital box diagram. How do these electrons go into the 2p?
One up in each.
One up in 2 orbitals, because you put, according to Hund's rule, 1 in each orbital before you pair them. Okay, so if we turn this into a carbon plus 1, it's going to be 1s2, 2s2, 2p1, right?
Yeah.
So it's going to look like this. So I'm going to circle this because that's the one that we take away to become carbon plus 1, right?
Yeah.
So I'm going to put IE1 here because that's the first ionization energy.
Okay.
Now I'm going to put IE2 here. And for carbon plus 2, 1s2, 2s2. And this is now empty.
Yeah.
So I'm going to circle that because that's the one we take. Okay, so can you see that we're going to take a 2p, and here we're going to take a 2p. Now, in reality, this is what's happening. So that's ionization energy 1. And that's ionization energy too. That's the reaction that we would write out, okay?
Okay.
Now, if this takes X kilojoules, this is probably going to take 2X kilojoules. And I'm going to explain to you why it's twice as much as the one above.
Okay.
Now, the reason is when you take a look at the separation of these two ions, you're going to judge the energy based on the charges. The larger the charges, the more energy it takes to separate them. And it's proportional to the charge. So I can multiply this as 1 times 1 and get X, right?
Yeah.
Well, 2 times 1 is going to be 2X.
Okay.
So this is going to be the case because they're both 2p electrons.
Okay.
Okay, so that's carbon. Now let's take a look at lithium, okay? So I'm going to draw a line across here, and I'm just going to try and fit lithium onto here. And so for lithium, we have 1s2, 2s1. And then to draw lithium plus 1, you draw 1s2. And here we're going to take a 2s electron, right?
Yep.
Hang on a second. Sorry about that. Okay, so we're going to take a 2s electron, right?
Yeah.
And then lithium 2 plus, we're going to get a 1s1. So here we're going to take a 1s electron. So here we're looking at a 2s versus a 1s. Do we expect them to be similar or dissimilar?
Dissimilar
Why?
because the difference in distance is greater.
Right. A 1s electron is much closer to the nucleus than a 2s, so a 2s should be much easier to take.
Yeah.
So here we would have to say this is going to be a greater difference because a 1s is, I'm just going to say, far more stable than a 2s. And that's because it's closer. Okay, so we have to make that argument for the rest of these atoms. So let's take a look at them. And, you know, now that we've done this for 2 of them, we probably don't need to do this sort of detail for the rest. But let's take a look at the others. And I've got to go back to my other screen. To see what other atoms we're looking at. So we're looking at nitrogen and beryllium, right?
Yeah.
Okay, so this is still number 7. For nitrogen, it's 1s2, 2s2, 2p3. And then to make a plus 1, it's going to be 1s2, 2s2, 2p2. And then to make an n plus 2, it's a 1s2, 2s2, 2p1. So here we take a 2p, and here we take a 2p, right?
Yeah.
And then for beryllium, it's 1s2, 2s2. So beryllium plus 1 is going to be 1s2, 2s1. And beryllium 2 plus is going to be a 1s2, 1s2. So here you're going to take a 2s, and here you're going to take a 2s. So when we put it all together for carbon, we're going to take a 2p, and we're going to take a 2p, for lithium, we're going to take a 2s and take a 1s. This has got to be the biggest difference because you're taking them from different shells.
Right. That's the easiest to explain.
That's, well, you say you're taking it from different shells, but you want to add a little more. You want to say, hey, you know what? Lower shells are more stable, which means the electrons are harder to take.
Yeah.
So, and also when you look at the 2s versus the 1s, I didn't draw this out, but if I write lithium plus ionization energy 1 gives you lithium plus 1 plus an electron, and lithium plus ionization energy 2, so lithium plus 1 here, turns into lithium plus 2 plus an electron. These are the two reactions that are happening. But this one is from a 2s, and this one is from a 1s. So here, these charges don't matter. I should say the charges are not the complete story.
Mm-hmm.
So this one should be twice as much as that one if these electrons were similar.
From the same shell.
Yeah.
Okay.
And I'm actually fibbing to you when I say that it's twice as much. It should be proportionally different.
Okay.
Okay, so that's all you would do for number 7 is, kind of show what's going on and then explain why these two are different. And ultimately, this is the explanation right here. I don't know if I have that lined up right.
So it's about the stability of what's being taken
Yeah,
and the correlating energy of that stability.
yep.
Okay. I'm
Okay.
yawning a lot.
So here, this one, would be part of the answer, but you'd also want to explain it, use some words. You don't want to just say, oh, there it is.
Right.
Okay. Okay, what's next?
I guess number 8 is really similar to what we had just done. So, right, because it's talking about the first and second ionization energies.
Yeah, it's very similar.
Yeah, it's basically asking the same thing.
But there's different reasons. So why is the first ionization energy of calcium greater than that of potassium?
Um, well, calcium ends in a 4s too, so you'd be taking from that shell.
Okay, so here, what I'm going to do with this one is I'm actually not going to start with argon. I'm going to start with neon.
Why?
You will see.
So you have more electrons to take.
Because I have more electrons to take. So here we're taking a 4s, right?
Yeah.
Okay. Now for potassium, we have neon, 3s2, 3p6, 4s2. No, 4s1, I'm sorry.
Yeah.
Calcium should be 4s2, and this should be 4s1.
Yeah.
Okay?
Yeah.
So here, this becomes neon, 3s2, 3p6, and you're taking a 4s. So they want to know, why does it take more energy to take one from calcium than potassium? They're both 4s's.
Yeah, I don't know.
So if the outermost shell doesn't explain it, what do you go to next?
Um, the nucleus.
Okay, so what about the nucleus are we interested in?
So calcium's nucleus has 20 protons versus potassium's 19, so it has a stronger pull.
Right. So basically the 4s is going to be harder to take from calcium because it's got 20 protons. Plus we know that size-wise, if this is calcium, this is potassium. Potassium's a little bit bigger because the protons can't pull the electrons in. And another way to look at it is, how close is the electron to the nucleus? The closer it is, the harder it is to take.
Yeah.
So calcium is harder to take. The first electron, because one, both electrons are taken from a 4s, but calcium has 20 protons, which holds the electrons better than potassium's 19 protons.
Okay.
Okay, so what about the second ionization energy? And now you're going to see why I did this.
Right.
So this is the first, this is the second. So now we have calcium +1 plus the second ionization energy. I should put ones up here. Becomes calcium +2 plus an electron. So calcium +1 is right here. Neon, 3s2, 3p6, 4s1, and it becomes neon, 3s2, 3p6. So we're taking a 4s.
Right. So
For potassium and its second ionization energy, we have neon, 3s2, 3p6, becoming neon, 3s2, 3p5. So we're taking a 3p electron. Now here, it doesn't matter that calcium's got more protons. In a fight to the end, the shell matters more than the number of protons.
okay.
Okay, so that's our go-to. You go to the shell first, but up here, when the shell that you take them from is the same, then what's your default?
The nucleus.
The protons in the nucleus. So you know how they say you've got an heir and a spare?
No.
In England, the queen has, she has two grandsons, right?
Yeah.
Prince Charles and Prince Williams. Well, Charles is the heir, and William is the heir, and the other guy's the heir. So you've got an heir and a spare.
Okay.
So that's a term you can share with other people. When they say, oh, you've got two kids, oh, you've got an heir and a spare, huh?
And then if the nucleus, if after that we would look at paired versus unpaired electrons.
No, sometimes you look at paired versus unpaired before the nucleus.
When would you do that?
We'll take a look at it. There's no example I've given you here in these problems, but we can take a look at one in a bit.
Okay.
Okay. Actually, number 10 might be the one.
Mm.
We'll look at
Oh.
number 10.
Ionization energy.
Yeah. Okay, so if we take a look here, we would say a 3p electron is much more stable than a 4s and therefore much harder to take. I'm going to say remove because remove sounds more sciencey than take. Okay.
Yeah.
All right. Any others?
No, I hadn't gotten to 9 and 10 yet anyway, so.
Well, let's take a look at 10.
Okay.
So we want to look at the ionization energies and rationalize them. So when we look at the periodic table, if this is silicon, this is phosphorus, this is sulfur, this is chlorine, and this would be argon, I think.
I don't have that.
Yep, I got lucky. All right, so when we look at ionization energies, we generally say when you go across, it's harder to take.
Yeah.
That's in general, right? Okay, but look at the values. We've got 787 here. We've got 1012 here. We've got 1000 here. And we've got 1251. So actually right here, there's a drop. It's not harder to take, it's easier. So let's examine each of these one at a time. So silicon, I'm going to go ahead and use the noble gas configuration. So that's going to be neon. 3s2, 3p2. So that also makes it neon. 3s2, 3p2. Okay?
Mm-hmm.
So which electron are we taking?
The farthest on the right.
Okay, let's do the same for phosphorus. And here's what I want you to do for me. I want you to get the electron configuration of each of these remaining 3.
Okay.
And I want you to write the orbital box diagram. And then I want you to circle the electron that you're taking.
Okay.
And I'm going to pause the recording. When you're done, let me know and I will resume the recording, okay?
Okay.
You're going to have to just sit there and listen to this all again. So if we take a look here at the differences here, the reason the phosphorus takes more energy than a silicon is because while they're both 3p electrons being taken, the phosphorus has 15 protons versus the silicon has 14. So you would expect the same trend for phosphorus and sulfur, right? Sulfur should be harder to take. It has 16 protons. But if we look at the number, it's actually a little bit less, or we're going to say it's about the same. So one way to look at this is that, you know, from silicon to phosphorus, it takes an extra 250 to take the electron. So from phosphorus to sulfur, we'd expect it also to be an extra 250, but it's the same. So what's the explanation when they're both 3p electrons being taken? And the explanation is this, that from the sulfur, you're taking a paired 3p electron versus the phosphorus, you're taking an unpaired 3p electron. Well, these two electrons in this one orbital, they're fighting with each other. They're trying to kick each other out of the orbital. And that's going to help you to take one of those electrons. And it turns out that how much it helps you is about 250 kilojoules here. So it takes you about an extra 250 kilojoules to take that next electron because it's 16 protons, but you save about 250 because it's paired. So it's about the same amount of energy. Okay. So when the shell is the same and the number of protons doesn't explain it, then you start looking at paired versus unpaired. And then next, when we look at chlorine, you'll notice compared to phosphorus, we're going up by 2 protons. So that should be an extra 500 kilojoules about, right? But you're taking a paired one, so that saves you 250 kilojoules. So it's going to cost you a net 250 more than phosphorus or sulfur. And there you get about 1250. So here, this one takes more than the sulfur because another way to compare it to the sulfur is that it has one more proton and they're both paired. And we can compare it to the phosphorus. The reason it's 250 more than the phosphorus is because you're going up by a charge of 2, but you're also doing a paired versus unpaired. So this is where you're going to take a look at paired versus unpaired, is when it's the same shell and the number of protons doesn't explain the trend. You want to start looking at paired versus unpaired electrons. And for most of these things, that means that you're going to look at the orbital box diagram, not the noble gas SPDF diagram, because the box diagram, it's easier to see what's paired and what's unpaired. We can certainly look at these and say, oh, there's only 2, none are paired. 3, none are paired. 4, 1 is paired, or 2 are paired, right? But you see how I just said, oh, 4, 1 is paired. No, 2 are paired. And I said 1 is paired because, you know, it's 1 more. And I go, oh, one's paired. But when you look here, you go, oh, 2 of them are paired. The box diagram is so much better than the SPDF. Okay?
Okay.
All right. And that was Charlotte listening to me talk about this for the second time because I forgot to record it.
Have a good weekend.
You too. Bye-bye.